Thank you very much. It's an honor to be here giving this one of the Simons Foundation lectures. And one of the occasions of I guess the main occasion of this lecture is that tomorrow we have our first annual meeting for the Simons collaboration on the non-perturbative bootstrap that was just mentioned. This is the logo of our collaboration, and it will appear again later in our slides. And so this will be one of the take-home messages. You see a girl with more or less horizontal legs and arms pulling herself up by her bootstraps, and similarly a boy who is doing the same thing but whose position is more vertical, and there's an equal sign, and that will be important. So today it's my privilege to give you this overview of the program of our collaboration, and towards the end of the lecture a little more by my own work. Our program is an approach, an emerging vision about quantum field theory. And so before I tell you about our approach, I think it's necessary to give you a crash course in quantum field theory, given this is a somewhat diverse audience. In fact, a little raise of hand. How many people here have a physics background? Oh, okay, so. How many don't have a physics background? But we can assume that those they don't have physics, at least have a math or computer science or general science background.
To me, you're completely inaudible. Am I alone in this problem?
I'm good. Okay, sorry. That's the best I got, but I don't know. Don't know how to fix this problem right now, but anyway, so let me start. So what is quantum field theory? Well, the first thing that you should know about quantum field theory is a universal language of theoretical physics, and in particular is the language of fundamental physics. So it's a language of particle physics. So in this first incarnation of quantum field theory, we have local quantum fields. So local here means that we have a set of functions, and whether the function or the function of space-time. There's a variable x includes both time and the three directions of space. And all of you are familiar, of course, with the electric and magnetic field. And in quantum theory, the ripples of these fields become interpreted as particles. And so for each particle pieces, we have a field. And the theory of all of elementary particles is sufficiently compact that to the extent we understand it today, can be written with a somewhat concise notation on a mug. And so, however, this first application of quantum field theory, which is in some sense the oldest and the most fundamental, is also the most abstract. And so I'd like to switch gears a bit and tell you about the second major application of quantum field theory, which will be important today. And apart from being interesting in its own right and being an important source of intuition, it's also more intuitive. So it will allow me to give you a more or less comprehensive course in quantum field, or what you will need to know about quantum field theory in 3 slides. So I want to start with something which you can visualize more easily. So we take a discrete system, for example, a lattice, a 3-dimensional lattice. At each point of the lattice, we have a little magnet. This is a famous model for a uniaxial ferromagnet. The little magnets can only point up or down. So clearly there is an up or down symmetry in the system, and at each point we allow the spin variable to have values plus or minus 1. I is an index that runs over all the psi lattices, which we assume to be very many. We take the larger limit. And the simplest kind of energy function that you can postulate is one where the energy is a sum over nearest neighbors. And so this is clearly a situation where if we take this constant to be positive, we are we're telling the spins that they should preferably align. So 2 neighboring spins will want to point in the same direction in order to minimize the energy. So this is the famous Ising model. And the intuition here is clear. Many of you have seen this before. Clearly, although the spins want to align, there's a competing effect, a competing disordering effect due to temperature. And so at very high temperature, the generic configuration will be random, and the spins will point in all possible directions, so that the average value of the spin is actually 0. The average monetization, the macroscopic monetization is 0. However, at low temperature, there are two completely equivalent directions, up or down, but the system, because of boundary condition or because of its history, will pick one of the two, and so there will, at low temperature, at 0 temperature, in fact, the spins will all be aligned either all up or all down, and so the system develops order, and intuitively, so we expect, and this can actually be proved rigorously, that there is some finite temperature known as a critical temperature that distinguishes between two regimes, where we have a macroscopic monetization, an average value of the spins, where the spins are on average order, or below TC, and above TC, the system is disordered. So near the critical temperature, intuitively, the system doesn't quite know in which direction it wants to point, and so a little disturbance, a local disturbance at one point of the lattice has a large effect far away. And so this can be formalized by saying that the correlation length is very large. And if the correlation length is very large, what makes sense to do is to go from this detailed microscopic description, in which you tell me the value of the spin at each point, to a sort of more coarse-grained description, where we take an average of the spins and describe this average in terms of a continuum variable, phi of x. And so we can replace, in this approach, due to Landau, this detailed microscopic model where we specify a given detailed configuration of spins and compute the exact value of the energy, with this approximation, this continuum approximation, where we integrate over all of three-dimensional space a functional of this continuum variable phi of x. And so this is, in some sense, for me, going to be my definition of a continuum field theory. If you're uncomfortable with the fact that we have a field phi of x that takes which is really an infinite set of variables, because for each point of space there is a variable, so it's an infinite dimensional system, always go back to the lattice description and imagine taking the limit. And then it's sort of clear that in the absence of an external magnetic field, we should write down the most general local functional of this variable phi of x, and so we write a systematic expansion where we add more and more powers and more derivatives, and these are the first few terms. And here you see that the coefficient of the phi square term is what controls whether we are above or below the critical temperature. If this quantity is positive, then the system wants to be in the ground state where the average monetization is 0, and if this quantity is negative, we'll have to decide to pick either the minimum where the monetization is positive or the minimum where the monetization is negative. Now, I want to elaborate a little on this description and tell you something slightly more sophisticated, which will shortcut a lot of beautiful theory, but in essence, I'm going to tell you the truth. And the truth is that, of course, here I'm neglecting an infinite tower of higher-dimensional operators, and I want the main message that is actually a sensible thing to do. So in physical parlance, and also in the ordinary meaning of the word, the higher terms that I'm neglecting, for example, phi to the 6, or two derivatives with phi squared, phi to the 8, etc., are irrelevant. This is, of course, a common word, but it's also a technical word, and irrelevant here means that their presence, whether or not I put them there, does not actually affect the behavior of the system so long as the universal very large distance properties are concerned near the critical temperature. And there is a simple rule of thumb that you can keep in mind. A term of this kind, a monomial of this kind, may be dressed with derivatives, which in physical parlance is called an operator, will be irrelevant if its weight is greater than 3. And here I have 3 because I am in 3 space dimensions. If I were to consider a theory in a higher or smaller number of dimensions, I would have to replace 3 with the appropriate dimension. And what is the scaling weight? Well, it's something we can assign by the following rules. The field phi is assigned dimension 1/2, or in general dimension d over 2 minus 1, whereas length are assigned dimension -1 and then create derivative dimension +1. And then you can easily convince yourself that all the terms that I have omitted are irrelevant in the sense that I have defined. In fact, there is a slight cheat because the phi to the 6th term in 3 space dimension have exactly dimension 3, and a little bit more sophisticated argument shows actually it's okay. It's actually irrelevant if you compute things in a more accurate way. And so this theory, which has been developed in great detail in the 70s by Wilson and followers, goes under the name of renormalization theory, and gives you a first hint, a first indication that it doesn't really matter which kind of microscopic starting point you take, precisely because this infinite tower of terms can be neglected so long as the critical behavior is concerned. And in particular, certain universal property of the system, such as the critical exponent, for example, the behavior of the monetization as we approach the critical temperature from below, there's a certain power beta, which is characteristic of the system, and in fact is universal. All systems in 3 dimensions that have this up or down system will have the same value of the critical exponent. There's a striking experimental fact, and we see a first indication of this in the fact that the details of which particular lattice system I start with are encoded in the precise coefficient of these higher order terms, but those are irrelevant. So, I've essentially defined quantum field theory for you. So what is quantum field theory? Is a theory of stochastic fields. It's a theory of random fields. And in the continuum limit, we are integrating over this random variable. There's one such random variable for each point in space with some measure. The measure before was this energy function that I wrote down earlier. And again, if you're uncomfortable with this continuum definition, go back to the lattice formulation I gave you and imagine taking the continuum limit. You're going to start to take the continuum limit where you send the lattice space into 0 while keeping the large distance properties fixed. And that's a well-defined procedure which goes under the name of renormalization. Now, again, I illustrated things in the context of statistical mechanics because they're more intuitive, and in that context, X is just space, and the fluctuations are controlled by the temperature. But we could also go back to quantum field theory, where then X is a point in space-time, and the fluctuations are controlled by h bar. So they would be thermal versus quantum fluctuations. Now, it's sort of clear from this expression that when G is small, you can perform a saddle point approximation, and things are under analytic control. Whereas where G is of order 1, or when G is large, this is a complicated object to calculate. So in some sense, that's a technical difficulty. We don't really know, in an easy way, how to calculate in quantum field theory when the coupling is not small. However, I'm transitioning here to our more abstract viewpoint, which is going to be the Bootstrap viewpoint. There are other more conceptual issues that you may want to consider in looking for a better formulation. And one of them is a very curious phenomenon that is actually ubiquitous in quantum field theory. We are learning more and more and more and more of these examples. And the phenomenon is the following. It might be that a certain statistical or quantum system has a certain formulation in terms of a certain set of fields, collectively noted by phi here, with some coupling constant G, but there is, in fact, an entirely equivalent. These are identical quantum theory with the same values of all possible correlation functions, where you have a completely different set of fields, which here schematically are denoted by prime, and a different coupling constant G prime. And schematically, it is such that when the theory on the left is easy, namely G is small, the theory on the right is hard, because G prime is large, and vice versa. And so here I'm using this famous drawing by Escher. So this would be a theory of weakly coupled trouts, and this would be a theory of weakly coupled birds. And yes, if the coupling is either small or large, you can use either one of the description, but this should make you feel a little uncomfortable, because the message here is that neither of these description really is a truly fundamental one. And in particular, if the coupling is intermediate valued, what am I talking about? So the description in terms of elementary fields, it's not both hard to use in the middle, and also given that different looking descriptions really describe the same physics, probably not the truly fundamental one. And we have also seen in recent years more and more examples of another even more striking phenomenon. Namely, we have evidence for theories, and here I would have to convince you that these are actual theories and not figments of our imagination. I will try to do that in a bit, in a few minutes, where we do not have any formulation in terms of elementary fields at all. Okay, so then you may ask, what do you actually mean by the theory? Well, what I will mean is a more abstract definition in which I'm able to calculate certain quantities in these putative theories, but I do not know how to obtain them by any kind of infinite dimensional functional integral of the kind I was writing earlier. And the prototypical example that I will mention later on is a somewhat exotic theory, perhaps from, if you have never heard of it before, but it's absolutely central in modern developments in theoretical physics, which is a six-dimensional theory which arises in string theory by considering the limit of solitonic objects known as M5 branes, known as the 2,0 theory. So then I'm transitioning now to our vision, which is, we are very grateful to the Science Foundation for having awarded us this collaboration grant. People in the grant, of course, share this common vision, but there are many others. We don't claim to be the only bootstrappers in the world. And this emerging vision is one that has been, in fact, around for decades, but now we have new ideas and new tools. And the idea is that rather than trying to do things in terms of a microscopic model, which you write down this field theory with the elementary fields and split it functionals and try to compute, you should try to characterize the space of all possible theories more abstractly. So the first intuition or message here is that you should enlarge the vision from trying to solve or study a single theory to the concept of theory space. That's a somewhat modern viewpoint about quantum field theory. Okay, of course, mathematically, this is going to be very hard to formulate precisely. We can formulate certain moving parts of it, and I will give you an example in a few minutes and ask again. So what we will mean by a theory, we will really mean a set of correlation functions. So I will prescribe a set of local operators, and I can there are values in different points in space-time, and I compute their endpoint average. And for me, this set of numbers, subject to various axiomatic consistency conditions, are what I mean by a theory. So the idea is that not anything goes. There are very sharp constraints that come from imposing the consistency principles of quantum mechanics and the various symmetries of the problem. And not only not anything goes, but we can use this general framework to put constraints that are so tight in some cases that with minimal additional physical input, for example, I told you later in the IC model I had this symmetry of flipping up and down. With minimal physical input, we can corner the theory of interest precisely. And so from this purely general axiomatic viewpoint, we'll actually be able to compute experimental numbers. So the ultimate goal, of course, would be compile a complete catalog of all possible theories. And so that's, of course, very ambitious. But anyway, that is the general program, which I will make concrete in some examples in a few minutes. And I wanted to mention the Wikipedia definition of the bootstrap. Of course, we know what bootstrap means in common parlance, but I like this definition very much. Wikipedia will tell you it's a self-starting process that is supposed to proceed without external input, and that captures precisely what we are doing. And the supposed to is also very important. You should not get too ambitious. Sometimes the fine print is important. You should read the precise declination of what you need to do, which kind of input you need to give to run this bootstrap problem is part of why we're studying this problem. Okay, so what can I possibly mean by theory space? So here is an intuition about theory space that all physicists, or at least all quantum field theories have, and let me try to convey it in this picture. So this is some sort of rough sketch of what I may mean by theory space. Of course, theory space is infinite dimensional. So I'm giving you a slice in theory space where I have two parameters, parameter 1 and parameter 2. And you see, I'm drawing a landscape where there is a height a third direction. And the third direction you're supposed to think of as some sort of a measure of the number of degrees of freedom of the theory. Okay, so clearly in this kind of picture there are extrema of this height function, which are either, that could be local maxima, local minima, absolute minima, saddle points, but extrema of this height function. And if the parameters are fine-tuned in such a way that you sit in one of those extrema, then what we are saying that we have a conformal field theory. What is a conformal field theory? I will explain this in a little bit more detail in the next few slides. But the idea is that it's a theory that looks the same at all length scales. There's no length in this picture. There's no length in this. Well, I'm trying to give you an intuition about theory space. So I'm trying. I'm trying my best. So early on, there was this parameter m square in my lection. There was the temperature minus the critical temperature. That is something that has units of length. So if I fine-tune that to 0, it turns out my theory has no intrinsic length parameter. And so you're supposed to imagine you're sitting at one of these extremal points. If I give an m square a little bit different from 0, either positive or negative, I slide a little bit off of this hill. And at that point, my theory acquires a length dependence. And what are these errors? Well, these errors are supposed to depict the flow of what happens in the theory at large distance. I'm integrating out the short length degrees of freedom and look at what happens at theory large distance. And the moment the intuition here is precise. Think about the classical particle sliding down this potential. The moment I'm a little bit off this maximum, I will flow down. And that is what in physical partners is called an RG flow. And the intuition, again, is you're integrating out the short distance degrees of freedom and looking at what happens in the theory far away. So if the theory has no intrinsic length parameters, if you're fine-tuning one of those values, you stay there. But the moment I kick you off a little bit by turning on what's called a relevant deformation, then you flow down.
Suppose there is background space. We want to say there is no background space.
There is definitely background space. So here, for example, I fix my background space with three-dimensional space. There is definitely background space, but the parameters of what I wrote earlier, my action functional, have units of length, except when they don't. And when they don't, I'm sitting at this extremal point. Okay? So that's the picture. Now, this picture can actually be made quite precise in 2 dimensions, and this height is called the C function. And so,
why is the number of degrees of freedom related to the RG flow?
Well, because again, the intuitive idea is that when you're integrating out short distance degrees of freedom, you're losing degrees of freedom. And so in this flow from top to bottom, you're losing degrees of freedom. That's why the RG flow is irreversible. You're flowing down. There's a very similar geometric phenomenon, as you know very well, in the theory of 3 manifolds, where you're flowing in one particular direction, and that
But why are the conformal field theories the critical point?
because those are, by definition, theories that are invariant under rescaling. And so here I'm giving you a physical example of a conformal field theory that comes again from the Ising model. And so this is something that you probably have seen, everybody of you have seen. Suppose we do a simulation of 2-dimensional Ising model, we tune ourselves precise the critical temperature. Now would be a good time to play the movie. So this is a Monte Carlo simulation of the Ising model, and we are looking at it at very different length scales. So these are simulations at very different length scales, and it turns out that they're just one inside the other. But at naked eye, you could not really tell the difference. All the 4 panels look the same. So on average, if you look at the statistical correlations, the system truly looks the same at all length scales. This is the sense in which a system is scale invariant. On average, if you look at these correlation functions, they are the same at all length scales. So at the critical temperature. If I am slightly off the critical temperature and I perform the same simulation, I would see that the system is very different as I perform this coarse graining, and that would be this arrow. I move in theory space because the theory now literally looks different at different length scales. So in this picture of theory space, then the task is sort of clear. The first thing is to understand the critical points. Those are the ones where we don't have an intrinsic length scale, so those are conformal field theories. And once we have developed a good understanding of these landmarks in theory space, we can start thinking about the flows. That's how we want to split the problem. And so the rest of our lecture will be focusing on conformal field theories. Okay? So I'm using the word conformal without having explained what it means. To mathematicians, of course, know what it means, but let me make it clear to those who haven't really seen the word before. Everybody understands what scale invariant means. It's the idea that we are performing a dilation, a uniform dilation x goes to lambda x. What is conformal invariance? I'm going to explain with a picture. This is another drawing by Escher. So this is a boy that sits in a gallery. The gallery is in a harbor, and the boy looks down the gallery. And then there is eventually, he looks at the painting in the gallery, and the painting contains the harbor, which contains the gallery, and so on ad infinitum. So there's clearly some very interesting global structure in the painting. But the reason why it looks sort of eerily okay is that locally, all Escher did was just this is the grid that he used to draw the painting. All he did was a slight rotation and a slight scaling of each of the squares of the grid. And so that's conformal invariance. It's a local scaling and rotation at each point of the grid. And although we don't have a theorem, and except in special cases such as two-dimensional unitary theories, it's been the experience of physicists that in all relevant physical examples, scale invariance is always enhanced to conformal invariance. Okay, so there are clearly, the story hasn't been completely cleaned up, but under reasonable assumptions, if you are at this point where there are no length scales, you can assume you have conformal invariance. In any dimensions, we think. Again, this is not a theorem. In 2 dimensions, under certain assumptions, is a theorem. In other dimensions, is barring sort of trivial counterexample, it's believed to be true. Such free theories. Okay, so finally, we get to something a little bit more precise. What is going to be my definition of this abstractly defined conformal field theory? Because remember, I want to move away from this word of explicit microscopic models where I start writing down energy functionals. My abstract definition is going to be a set of gadgets of this kind where OK of x is abstractly defined list of operators. Okay? In the example I had earlier, what are these operators? It would be m squared, m cubed, m, two derivatives, m, etc. All possible monomials built out of the element, I call the field phi. All possible monomials built out of phi and its derivatives. Those would be the operators. But more abstractly, I just give you a list of indices, if you will, that parameterize my set of operators, and I require knowledge of all of their endpoint functions for arbitrary value of the space or space.
L2 of your background space. So operator acting on L2 on the background space. Where they define.
I'm using the word operator here in the way I defined earlier. So operators here, don't think about them as actual operators because that's going to be very confusing. They will become actual operators if we view it in a different language. Here, think of this in the context of statistical mechanics. This is a local disturbance of the system, and I just look at their correlations at different points. So in terms of the elementary field description I had earlier, these are just local functions of my field, such as phi square, phi cube, etc. I compute this correlation function by weighting these monomials with the measure that I had. It was e to the minus h. Okay, so think of this just in the context of statistical mechanics because it's easier. It's an operator for good. It's called an operator for good reasons, but I don't want to discuss that why it's an actual operator. So, in the context of the Ising model, for example, we can have the operator that just describes locally what is the value of the spin at each point, or what is the value of the energy. But in fact, those are the easy ones to describe in words, but in fact, I can list an infinite number of operators that describe more complicated observables I can build out of the elementary spin, and clearly there is an infinite number of them. And so my definition of the CFT that describes the Ising model will be the list of these local operators. And for the Ising model, what do we know? Well, one thing we know for sure is that there is this up-down symmetry. So we can classify operators according to whether they're even or odd under this symmetry. So the spin operator is this little arrow. Clearly, if I flip it, changes sign. So sigma would be odd under this Z2 symmetry, where the energy, which was a bilinear in the spins, it's even under this Z2 symmetry. In more complicated example, you may have additional, possibly non-abelian symmetries that are additional quantum numbers that you want to assign to your list of operators. And then one can show that if the theory is supposed to be conformal invariant, then the two-point function must have this universal form in terms of a quantity delta, which is specific to the operator. So the operator comes with a certain quantum number, a certain intrinsic property, which is a real number delta for each operator, such a two-point function behaves this way. And these are the numbers that are directly related to the critical exponents of the statistical system. I gave you here the example of the exponent alpha, which was the one for the specific hit. Now, the crucial fact about conformal field theory, which distinguishes it from more general quantum field theories, where you can define a similar structure, the crucial fact is that this list of operators has an algebraic structure. So if I take two of them at different points in space-time, I can expand them into an infinite sum over the runs over all the operators of the theory with certain structure constants and with a certain dependence on the coordinates, which is fixed by requiring that the weight under scale invariance works out correctly. Remember that the coordinate had weight -1, and then you can check that this is the correct scaling. So what do I mean by this equation? I mean the following, that I'm able to use this inside any correlation function. So if I have the correlation function of 4 operator, or 1, or 2, or 3, or 4, I can take the first two and replace it with an infinite sum of this kind. I can do the same for the third and the fourth, replace it with an infinite sum, and then evaluate the two-point functions using this kind of equation, and I'm done. So it's clear that by iteration, any n-point function can be reduced using the operator parameters function to an n-1 point function, and finally, eventually, you get to the correlator of a single operator, which, because the system is scale invariant, is 0, unless the operator is just the identity. And so by iteration, you can compute any n-point function algebraically using the structure constants. N-point correlations. Okay, so it's clear that, at least in principle, the entire content of the theory is fixed by the value of these deltas and the value of the structure constants. So this is starting to look like an algebraic structure, not too different in spirit, vaguely at least, from the kind of algebraic structure we encounter, such as Lie algebras, or we have some sort of bracket operation, some sort of three-point operation encoding the structure constant, and if we were clever enough, we could perhaps just classify this kind of structures algebraically. Now, the crucial point here that I want to at least spend half a minute here is if I give you a 4-point function, there is a finite region of the values of the 4 coordinates where the sum converges. It's absolutely convergent sum. Okay? So this would be not generically the case in a non-conformal quantum field theory. The sum would just be asymptotic. In a conformal field theory, this is an absolutely convergent sum for a finite region of the values of the coordinates, and then once you have it in a finite region, you can analytically continue. And then the idea sort of presents itself very naturally. Clearly, a basic consistency condition is that if I start from a 4-point function and I do this fusion in different ways, if any of this is going to make any sense, I must get the same result. And so I should be able to fuse operator 1 and 2 together and 3 and 4 together in this channel, or vice versa, do it in this other channel, 2 and 3 and 1 and 4 together. And this is, of course, the logo that I had earlier. I must get the same result. So this is what physics call crossing symmetry, and you can also, in more mathematical parallel, it's just associativity of the operator product. The operator must be associative, and so this operation is associative, so the order in which you perform it should not matter. And it's important for this to make sense that the left-hand side, the right-hand side have a common domain where they're both absolutely convergent sums, which is indeed the case. And then this becomes truly it's a true equation that the structure constant of the theory must satisfy. And so you can hope from here that this will be very constrained. It will actually determine a very strong constraint of what kind of deltas or what kind of CIJK you can have. This is an old idea that goes back to the 70s. And it met, as I'm sure many of you have heard, a spectacular success in 2 dimensions. Not for all theories, but for a significant subset of 2-dimensional theories, this program leads to a complete solution. And the reason is that in 2 dimensions, the conformal algebra is actually infinite dimensional because it's the algebra of holomorphic reparameterizations. And the algebra being infinite dimensional, it turns out that these operators I had earlier that were infinitely many, in some cases, not always, but in some cases can be organized into a finite number of families, into a finite number of representations of the conformal algebra. The number of operators is always infinite, but in some cases, given that the algebra in 2-dimensional is infinite dimensional, I'm able to reorganize them into just a finite number of representation of the conformal algebra. And though the equation that I have, they look like an infinite system of equations, but thanks to the power of this infinite symmetry, they just become a finite system of equations, which can then be solved. And this is precisely what happens when this variable c that I had in my picture earlier, that is some sort of a measure of the number of degrees of freedom, is smaller than 1. In that case, it turns out, you can achieve a complete classification of solutions of this set of equations, which can be said very simply. There is one theory for each integer p, which for historic reason starts from 3. And the theory with p equal to 3 is the conformal field theory corresponding to the Ising model. For p equal to 4 is something else called the tricritical Ising model. For p equal to 5, the 3-state Potts model. And then you run out of names, but there is an infinite sequence all the way up to p equal infinity. Okay, so here there's an assumption that I'm putting in parentheses because I haven't really explained it yet. These are not all possible theories, they're the unitary ones. And unitarity is very natural if we're looking at theory in Lorentzian space, because in that case it's related to the fact that we're doing quantum theory, and so there's probabilities are positive. In statistical mechanics, it is actually not mandatory, and so it's perfectly okay to look at theories which are not unitary. But for the sake of simplicity here, I just gave you the classification for unitary theories. Even in 2 dimensions, if the number of degrees of freedom is greater than 1, then the story is complicated. There's no such simple statement you can make. But nevertheless, this is the paradigm of what we would like to do more generally. A complete catalog. It's a little bit like classifying the crystallographic point groups. Once you've done that, you know you're never going to find a crystal with a specter that you can recognize, because you've classified them once and for all. There are 32 of them.
It
It doesn't work. There are quasi-crystal, of course. I mean, like all good no-go theorems have exceptions, but under a certain set of assumptions, you prove a theorem, and similarly, we would like to do something like that here. I want to emphasize, so what this catalog of tells you to dimension, it computes for you the critical exponents of an infinite number of systems, regardless of where their microscopic definition is. And so the holy grail is to repeat this success in higher dimensions. Now, this is something that has been possible only recently, since 2008. And the idea is to trying to be a little bit less ambitious than finding exact solutions, as one can do in 2 dimensions. You want to use this infinite system of exact equalities I had earlier, combined with the fact that this coefficient Cij must be real. That is this condition of probabilities being positive in a quantum theory, which means that their squares are positive. And you start from this infinite set of equalities with positive number, and it's hard to solve, but you know that if you truncate the system, you neglect some terms, you don't know what they are, but you know their sign. And so this leads to an approximation scheme in which you don't quite aim for an exact solution, but you aim for finding a set of inequalities in this formal space of possible data. Okay? And at first, this sounds like too drastic of a retreat, because, okay, well, if it's just an inequality, what am I going to do with it? But the great surprise that we're still absorbing, and we don't really understand why things are working so well, is that if you input just the right kind of information, for example, in the case of the Ising model, the fact that I had this up-down symmetry, with just the right kind of input, the inequalities are so stringent that, in fact, corner the theory, we think, in the limit in which we numerically run this program to infinite precision exactly. So the idea is that at any truncation, I have a true statement. It may not be optimal. And what we are finding experimentally is that as we increase the number of constraints, we are converging to what seems like a unique solution. So let me give you our flagship result, which is precisely carrying out this program for the 3-dimensional Ising model. I do not start with any lattice model at all. I only have the following assumption. The theory is conformal. It lives in 3 space dimensions. And there are precisely 2 relevant operators. Remember, I had the distinction between relevant and irrelevant. The relevant operators are the ones that allow me to flow down the hill. And experimentally, how do we know that there are 2 relevant operators? Well, because if I want to tune myself at the critical temperature, I need to dial 2 experimental knobs. First, to the critical point, there are 2 experimental knobs I need to dial, the temperature, but also the magnetic field. I need to set the magnetic field to 0 and dial myself at the critical temperature. That's enough to reach the critical point in a ferromagnet. And so that means that I have precisely 2 relevant operators, because those are the directions I need to tune in this theory space to be at the critical point. All the other directions are irrelevant. And so just the fact that the phase diagram of the ferromagnet is 2-dimensional tells us I have precisely 2 relevant operators. One which is odd under this Z2 up-down symmetry, and one which is even. So these are the only assumptions that go in making this plot, nothing else. And then you find, numerically, but again, this is a rigorous kind of numerics. It's not optimal, but it's at any given order of approximation is a true fact. You find that the dimension of the leading odd and the leading even operator, let me neglect this region here, which can be excluded if you know that you are more or less in this vicinity. If you more or less tell me that the critical exponents are of the order of 0.52, then you find that the constraints that come from crossing tell you that this might lie in a tiny island, which in fact here is even bigger because otherwise it would not be visible. And you find the critical exponent of the Ising model with 6 digits from pure thought. nothing went in this plot except the assumption that I made. There was never a microscopic model written down, ever. And so this is the proof of universality. Of course, the critical correspondence is universal because it's a unique theory with the requisite symmetries. It's a proof, quote unquote. We don't really know that as we improve our numerics, the Eisen is going to shrink to 0. But already with present accuracy, this is the world's best determination to critical correspondence to the Eisen model. It beats Monte Carlo. Okay? So then the idea is that we take this as an inspiration to go forward. And the program is, of course, a very ambitious program. And we will never really complete it. But the idea, this is the Platonic idea that we would like to achieve, chart all of theory space, starting from the conformal fixed points. So how can we organize our search of theories? Well, one way to do it is to work up in the number of relevant operators. I mean, the theories that are relevant for the real world don't have infinitely complicated phase diagrams, right? The more parameters you need to tune, the less likely is for this theory to be relevant in the lab. And so we call this the CFT genome project as an internal nomiker, which is finding the list of all CFTs with a small number of relevant operators. Now, of course, given that some of us have more of a math physics background, there's another obvious thing you want to do, which is add enough symmetries to the problem, and in particular, add enough supersymmetry to the problem, to turn this classification problem into something that has a nice mathematical structure, and it is in fact tractable and possibly exactly solvable. And so in particular, my work has been, a lot of my work is focused on the idea of trying to chart the space of theory which are both conformal and supersymmetric. Now, unfortunately, I don't have the time to give you a review of supersymmetry. It would take a whole other hour, but you may have heard of it. It's a fermionic symmetry. You go from algebra to superalgebra. It's a symmetry that relates boson and fermions. And it's a bit of an acquired taste, but certainly if you are a theorist, you start loving supersymmetry very soon because you get amazing results, and it's I cannot emphasize enough how these kind of theories are really central to modern mathematical physics. And then this leads to a classification problem of theory that are both conformal and supersymmetric, and we may hope that at least for maximal supersymmetry or enough amount of symmetry, this could actually be a completely solvable mathematical problem. A first hint that there's something nice here is that these theories, one can easily prove, have an upper dimension. You cannot have superconformal field theories above 6 dimensions because there's no requisite superalgebra. An algebra that contains both conformal generators and supercharges stops to exist in 6 dimensions because you need certain sporadic properties of spinors that stop making sense above 6 dimensions. And so we have now a program of classifying these theories, and in particular we have found that although this complicated system of Bootstrap equations in general can only be handled numerically, there are subsetters of the equation. There are some particularly nice operators which in supersymmetric parlance are called BPS operators or chiral operators, or there is a subsetter of operators that close among each other. They form a subalgebra of this infinite dimensional algebra, and that is something which is in fact amenable to a completely rigorous mathematical characterization. And so in particular, we find lurking in this complicated algebra operator structure that mathematicians have defined to their complete satisfaction, such as, for example, two-dimensional vertex operator algebras. And so I want to now to give you a little bit of flavor how this works. Going back to this example, to this theory I had mentioned at the beginning, which is the paradigm of a theory for which we have no traditional field theory formulation whatsoever. Okay? There's simply no way in which we can write down, with present understanding, an energy function of the kind that I had earlier, h of phi, and integrating over these random fields phi that defines the theory. The theory is also singled out because it is the one with maximal amount of supersymmetry in the highest number of dimensions. So in terms of the most supersymmetric theory of all, if you will. And so what do we really mean that we have a theory? Of course, the evidence is indirect. And in particular, the theory was discovered from string theory or from M theory by taking the limit. So there is this theory that we believe exists. It's a quantum gravity theory in 11 dimensions. It's called M theory. And it has various solitonic objects. In particular, it has objects that are 5-dimensional space directions and 1-time direction. They're called M5 branes. M is the same as M theory. And the low energy dynamics of a stack of n of these 5 branes is believed to be a well-defined field theory, which is precisely this mysterious 6-dimensional 2,0 theory, which is parameterized by this integer n. So what do we mean that the theory exists? Well, we have indirect ways to argue from string theory and from M theory that the limit is well defined, that in this limit we can decouple gravity, and that we can then define, at least in principle, this correlation function of certain local objects. But we have no way of constructing this abstract local object in terms of some more elementary fields, because there's no such thing. And in fact, if we go back to this intuition that I had given you earlier, this simple rule of thumb for power counting, you can sort of understand why it would be so hard to construct such a microscopic action in dimension greater than 4. And the reason is that in 6 dimensions in particular, the naive weight of phi, the one that you assign to phi if you started from a free theory, is 2. And so the simplest operator that is that will give you an interaction that is not a Gaussian naive thing like phi squared would be phi to the 8, but phi to the 8 is irrelevant. And so just power counting tells you that you're never going to be able to obtain this theory as the low energy limit starting from some well-defined UV theory where you know the rules of the game. Of course, that could be a more complicated UV starting point, but then we don't know what to do. Okay, so this is a simple heuristic argument to tell you that it's unlikely you're ever going to find some simple 6-dimensional lattice description or microscopic description of this theory. And the other major reason why this theory is so central to developments in mathematical physics is that the moment you take the 6 dimensions where it is defined and compactify some of them, you take the 6-dimensional space to be a product space where, say, 4 dimensions are 4 and 2-dimensional Riemann surface or something more complicated than that, and you go at low energies in the non-compact direction, you find a huge landscape of theories parameterized by the shape over which you compactify the theory. And by this route, you generate, I don't want to say all, but certainly a huge number of very interesting lower dimensional supersymmetric field theories. And the other final reason why this theory is important in the context of string theory is that although for phi and n we don't really have any other way to access it except for the bootstrap, there's this remarkable conjecture that says in the limit where n is large, the theory becomes completely equivalent to a theory of classical supergravity in 11 dimensions, but not in flat space-time, in a product space-time, which is ADS 7, the 7-dimensional space of negative curvature, symmetric space of negative curvature times the 4th sphere. And this is possibly the most mysterious and the most dramatic manifestation of this duality principle I had outlined earlier. Remember the Escher picture where we had the theory of weakly coupled trouts, of weakly coupled birds. One duality description of the theory is in terms of gravity. Remarkably enough, the theory of quantum gravity in this space is believed to be entirely equivalent to the 6-dimensional theory that contains no gravity. Okay, so that leads me to basically, I don't really have now the story will become very technical, but basically the bootstrap is the only game in town. This theory is mysterious. We can only characterize it from its symmetries. And the take-home message, the symmetries appear to be powerful enough to completely define it. And we can do this in 2 steps. Step number 1, we can identify a nice subsector, which is exactly solvable. What is the physical input here is something that we have to take as a given. It comes from our knowledge in string theory. There is a certain tower of operators which belong to a certain representation of the superalgebra whose dimension runs from 4 to 2n. So if n equal to 2 is the simplest case, and n going to infinity, there's an infinite tower. And knowing that these operators exist and they have a certain representation theoretic properties, we can find a larger class of operators which are also going to be exactly tractable, that contain this as a subset. And this larger class of operators is such that if I put them all in a plane, I choose a plane in the 6-dimensional space, and I parameterize my plane by complex coordinates z and z bar. A priori, this would be, of course, a function both of the zi and the zi bar, but it turns out that one can prove, using a certain cohomological argument, that is in fact just a meromorphic function. And so those of you who have seen this before will recognize the structure of a 2-dimensional vertex operator algebra. And in fact, we can decide from symmetries alone that this is nothing but the Wn algebra, generalization of the algebra of Zamolodchikov. And so we get to compute these correlators purely from symmetries, because we can compute the correlator of the Wn algebra by closing the Bootstrap equations. And then the icing on the cake, that if we take the Lagrangian limit, we recover the structure of nonlinear supergravity on S5 times S5, which is quite striking. Now, for the rest of the operators, step number 2 is the operators that are not so simple, for which we don't have a mathematical tool. And for them, however, we can play exactly the same game we play for the 3D Ising model. We can play these games of island shrinking. And we have numerical evidence, at least for n equal to 2, but we believe that with more input we can do it for all n, that the theory is uniquely defined. And so I find this rather striking. The theory doesn't have any other intrinsic definition, but we have a blueprint, we have a scheme to define it from symmetries alone with minimal amount of information. And so this is a numerical plot, and the values, so delta 0, delta 2, and delta 4 are certain operators, spin 2, spin 4, spin 0, which are not in this nice sector where we can compute everything. And the actual value, we believe, is given by the corner of this golden nugget. OK, so I'm essentially concluded what I wanted to tell you, so I want to recap the main message here. Sorry, I forgot. I have one extra slide, which is I already mentioned the main idea here. The main idea here was what I said earlier, that we can take the theory on a product space of this kind, a Riemann surface possibly with decorated points, with punctures. And as we look at large distances in the non-compact space, we find a theory with n equal to 2 supersymmetry in 4 dimensions. And now we have a whole space of theories parameterized by the shape of the curve. Okay, so this is yet another sort of game you can play with theory space. Now, theory space has become an actual space, an actual real physical space of my in this higher dimensional world. And now you can play a game of decomposing this Riemann surface in different limits, and as you glue it back in a different way, you can argue that certain observables only depend on the topology of the surface. And so this leads to the definition of a topological quantum field theory, because only the topology of the surface is relevant, valued in vertex operator algebra. I told you that for any theories of this kind, I have a vertex operator algebra, which is this nice subsector of operators, and now I have one such nice subsector for each of these shapes, and gluing back the shapes in different ways, I must find the same vertex operator algebra, and then this leads to a very interesting, purely mathematical development that Arakawa has worked on, proving some of our conjectures. Okay, let me recap. So I told you about theory space. Don't try to solve a given theory, enlarge a view to the space of all theories. And I told you that it's fruitful to use internal consistency rules and symmetries to chart the space without solving detailed models. And so the dichotomy here, I mean, the old method is still useful for certain purposes. Sometimes we want to just build a detailed dynamical model in which we identify what the microscopic degrees of freedom are, and we write the theory and then solve it. But perhaps the meta question is sometimes more fruitful. What are the theories that were in principle allowed? And it turns out that not anything goes. The symmetries are very constraining, and in particular, if I have general symmetries together with a specific symmetry of the problem, I can get a lot of mileage. Ideally, we would like to find a complete catalog of consistent theories, but the Ising model was one case where we didn't have to find a complete catalog, because minimal amount of information that we know for sure to be true was in fact enough to completely determine the answer. Thank you.